So we can probably start. Last time we defined what is Lie derivative. I explained what is the motivation for it and what is the definition. Lie derivative of arbitrary tensor field is d over dt over 0 phi t star a, where phi t is a flow associated with vector field v. Yes, so I explained that the idea is that we pull back, we have mv, integral curves of this v, and we pull back a given tensor field backwards against the flow and compare with the tensor which is not pulled back, and the difference is interesting measure of how the tensor field changes along this flow. Yes, so Lie derivative computes the rate of change of vector field as we go along the flow. If it is invariant with respect to the flow, so Lie derivative will be 0. Now we want to have a tool how to compute Lie derivative in components. So have a look what we need. Or first, what is the Lie derivative of linear combination and tensor product? So here are important properties of Lie derivative, that how it behaves on linear combination and tensor product. It is interesting in its own sake, but now we need it in order to compute the component expression, that how to do it. And so in order to do, for example, the product, we need, as we see, how pullback behaves on product. But we already discussed it when we studied pullback. Now recall that this is a pullback with respect to a diffeomorphism. So the simplest pullback, that it simply acts on each term. And similarly, linear combination. Yes, linear combination. It's even simpler. So the second line means that this pullback is a linear operator on tensors, on tensor fields. And the first, that it preserves the multiplication. So altogether it is a morphism. Yes, it preserves linear combination and tensor product. And now, what does it mean for this derivative? For example, here, that what about d over dt at 0 of this expression? So it is it is a product, and especially notice that if we write this in components, it will be simple product of functions. Yes, so we can apply the Leibniz rule for making this derivative, and it means that it is d over dt of the first guy multiplied by evaluation at t equals 0 of the second one, plus evaluation of the first one multiplied by d over dt at 0, the second one. So here we have Lie derivative of just A. Here this is identity on tensors. So altogether it is just B. The same here, A and Lie derivative of B. So we see that Lie derivative of A cross B equals Lie derivative of A cross just B plus A cross Lie derivative of B. So Leibniz rule. And from the second line, very similarly, we notice that if pullback is linear, then also Lie derivative is linear. So very important properties of Lie derivative, that it behaves nicely. It behaves according to Leibniz and as a linear operator. And now imagine that we want to compute Lie derivative of arbitrary A. So it is Lie derivative of components A, I, J, K, L, dx k tensor product derivative with respect to J. So what we see here, it is summation over indices. That means we apply the second line. And then each term is a tensor product of many other terms. So we apply the first line of these two properties. Yes. So what we obtain, it is Lie derivative of the first, just apply Leibniz, but iterated Leibniz. A, I, J, K, L, and dx k derivative with respect to J, plus nothing with ij, kl, Lie derivative of dxk, and nothing with other members, 3 dots, plus the last one will be Lie derivative of the last basis element. I, J, K, L, dx k, Lie derivative of J. So we see that in order to compute Lie derivative of any tensor field, we need just 3 things to compute. Namely, what about Lie derivative of a function? It is here. Here, Lie derivative of basis coordinate covector and basis coordinate vector. 3 results. And we will prove from some other property that actually just 2 objects are needed. The first one is function. We will compute it explicitly from the definition. And then either that or that is enough. Not both are necessary. You can do both from the definition, but it is not necessary. One of them should be done somehow, and the other one from some property. Now, what is the property? Or maybe, no, I will go to this property. It is that pullback So first, yes, this pullback with respect to a diffeomorphism of unit tensor is a unit tensor. It was proved on exercises, I think. That pullback of unit tensor is invariant with respect to any diffeomorphism pullback. So this means by d over dt in 0, that Lie derivative of this tensor is 0. Yes, because it doesn't depend. It is invariant. It doesn't depend on t. Now, remember that the bracket alpha v can be written as contraction of alpha and tensorial v, tensor product. Or better, okay. Yes, it is like that, and at the same time it is unit tensor on v and alpha. And also we need a property of pullback. The general strategy is that recall the properties of pullback and compute from it properties of Lie derivative, because Lie derivative is d over dt of some pullback. Yes. So, for example, like here, from the properties that how behaves pullback, we computed how necessarily behaves Lie derivative. So, one of these properties is that pullback commutes with contraction. Any pullback of diffeomorphism, not just this flow, yes? But if you have any diffeomorphism, there was an exercise, it commutes with contraction. So including this diffeomorphism. So we can, for example, start from this equation that what about Lie derivative of alpha and v so it is d over dt at 0 of phi t star pullback of this expression because it is alpha v. Now, because pullback commutes with c, it can be written as contraction of d over dt at 0 of phi t star applied to the tensor product, which is applied at the same time on alpha and v. And this is just a special case of tensor product. So we have Lie derivative of alpha cross v plus alpha cross, oh, sorry, there are two v's. You see, I didn't notice that. Let's put it w here, because here is also v. So now we have this Lie derivative gives us v, and here is w, another vector field. So Lie derivative respect in direction of v of w. Here is also w. And contraction gives it back to the form of the bracket. So it is LV alpha and w plus alpha LV of w. And what we see from it, that if we are able to compute function. Here is function, yes, on the left. And one of these guys, we are also able to compute the second one of these guys. Yes, we will see that here is Lie derivative of covector, here is Lie derivative of vector, but in the bracket with arbitrary alpha and arbitrary w, we will see that application of these two basic elements gives us from one of them the second one. Either this we compute and then this is trivial, or this we compute and this is trivial from this property. I will come it now because we see already that we need to compute Lie derivative of a function. So let us do it. Let's psi be a function. So it is T00 type tensor. So what is Lie derivative of a function? By definition, it is this pullback. But now, what is pullback of a function? It is just a composition. So when we compute this function at a point M, what we get? d over dt at 0 function at phi tm. Yes, but what does it mean? Here is the flow. And we have a function now, which is R-valued. So what we are computing here? Psi is computed at phi tm. So if here is m, here is phi t of m. Yes. So what we are computing? We are computing the directional derivative of this function in the direction of this flow. But what does it mean? The flow was generated by v. So the derivative along this particular flow is just application of v on c at m. Yes, because this is directional derivative. And we need to compute, as we see, the exactly directional derivative in the direction of the flow. So we see that this is very simple technically, that if you want to compute Lie derivative of a function in the direction of v, just apply v on the function. It is that simple. So we have already the first step. Yes. For example, here we need to compute Lie derivative of this function. So it is v applied on ijkl. And what does it mean? V applied on ijkl, because v is what? Ijkl some m, derivative with respect to m. In coordinates, it is vm ijkl comma m. In detail in coordinates. Yes, but it is also nice to write it in this way. So we have already the result, how to compute the first member of what is needed for any tensor. Yes, we know what about this term of component. Just apply v on this. Now, this is also simple because of some property of pullback. And what is the nice property of pullback? Now, that pullback commutes with gradient operator on functions. We had it. I think that also in exercises, maybe there was some commutative diagram for it. I remember that it was done on exercises, yes? So this is a very, very useful property now, because what does it mean? Apply d over dt at 0, and you notice that Lie derivative commutes with d. Extremely important property. So from here, we have that Lie derivative commutes with C, and from here that it commutes with D operator, gradient. So now we want, I will write our results. Now we want to compute this guy here. That's the second necessary, and then the third one. So because now we learned that Lie derivative commutes with d, it can be written as d of Lie derivative of a function xi. Yes, it is a Lie derivative of a function now, coordinate function. So we already know from here, what is it? It is application of v on xi. But what is v in coordinates? vk derivative with respect to k. This is a first order differential operator. So what we obtain? Derivative with respect to k of xi is delta ik. So from this we have vi. It is d of, so this is vi, so this is d of vi. But what is it? It is a gradient of ith component of this vector field. And how the gradient is computed? Vi, k dx k. So we have result that Lie derivative of dx I is vi k dx k. In general, Lie derivative of psi, of d psi, sorry, is d of v applied on psi, and this is 3 dots. It can be easily computed, yes, but we need only now these coordinates. And now the last one. What about this? Yes. So we can now use this property, this equality, and we will compute it on special arguments alpha and w, namely on dxi and derivative with respect to j. Okay, so we are repeating this computation here for general alpha and w, for alpha equal basis alpha and w equal basis w. So first, this is a function. We need to compute the left-hand side, right-hand side, and then make some profit from it. The left-hand side is just a function, and we know what about the Lie derivative of a function from the first line. So what function is here? It is function delta ij. It is constant function, which is just 0 and 1. So when you apply Lie derivative, which is just v applied on delta ij, because v is differential operator, it is 0. So left-hand side gives us 0. But the right-hand side gives us, by this Leibniz, that it is Lie derivative of dxi on derivative with respect to j plus dxi on Lie derivative with respect to j of partial j, yes? Now, what are these two terms? Here is some covector, and here is covector evaluated on basis vector. What does it mean? It is a component, jth component of this covector. It is by definition of component. Plus, the same story here, it is ith component of this vector. So we have the sum of some components of the covector plus the components of the vector is altogether 0. So this is minus this. Yes? Now we need this one. So I will write that Lie derivative of partial j, its I component is minus Lie derivative of dxi j component. Now what is it? We see the computation of what is Lie derivative of dxi. Here is the result. So what is its j component? It is the guy which sits near dxj. Yes? So it is vi comma j minus vi comma j. And then what is the complete expression? It is the ith component plus basis. So it is minus vi j derivative with respect to I. So here I will write finally minus v, here is I, comma I of some j. So the important results are this one, and this one. These results already enable us to compute Lie derivative in components of any tensor field. So let's do it for 1-1 tensor, because in 1-1 tensor you already use all those results. And we see that what happens for general tensor. For general tensor, just several times happens what happens once in 1-1 tensor. So do it in detail. This is Lie derivative of any 1-1 tensor, yes? So first, Lie derivative of components. It is application of V on these components. And nothing with basis. Now, plus nothing with components and Lie derivative of dxj, and nothing with the second part of the basis, plus components dxj times Lie derivative of the last object. It's 3 terms for 1-1 tensor. this in detail is aij, comma, k, vk. Here, we have from here the result vj, comma, k, dx, k, and here we have minus, from here it is just I, so minus v k, comma, I, derivative with respect to k. And now we want to sum it together. So let's write the second and third term all together with these indices, yes, these indices on basis. So first it is v applied on aij plus something from here minus something from here, because here is minus, and the end should be dx j and derivative with respect to I. So here we already see the term. Here it is similar, but instead of j we have k here. So we should rename jk indices on this expression, jk, so it should be ai k v k j, and then dxj and derivative with respect to I, because now it is dxk and I. And here j, this is okay, but here we j is okay, but here should be, instead of k, it should be I. So renaming I and k gives us minus k j ki, yes, so hopefully this, does it work? Yes, it seems so. So then, what is this? Or what we did is LV of A. Here is A decomposition. What we get is something in the long in the bracket and then the basis. So this should be the derivative of A, the thing which we want to compute, ij. Now imagine that we have no 1,1 tensor, but 1,2 tensor. What happens? 1,2 tensor means that two lower indices, that means 2 times this dx. That means 2 times something like here, additionally, yes. So 2 terms like that and 1 term like that. So, and what about tensor 2, 1, 2 terms like that and 1 terms like that. So in general, for each lower and upper indices, 1 term of very specific structure. Yes. So here the specific structure is already clear, and it is written in the book as a table that if you want to compute Lie derivative of A, which has several upper and several lower indices, do the following. First, apply V on your components. This is always there. And then, depending on how many indices are upper and lower, add 1 term for each upper indices and 1 term for each lower index. One with plus, the other with minus, the structure is here. So now it is completely routine way how to compute Lie derivative of anything. So it is already already the end of the practical side, that do you want to compute Lie derivative of any tensor field? Do you know its components with respect to coordinate basis? Then there is a table that count how many indices you have upper and lower, and apply this table. Here, just one for upper, one for lower. So, for example, if we need to compute Lie derivative of metric tensor, so the result is ij. So there are two terms of the similar like the first guy, yes, because there are just two lower indices, gij. So this part of the story is there, and this part of the story is not present. So this minus is not there, but there are two pluses. So what is there? It is v applied on gij, and with two pluses, there are some two terms. Here v is not differentiated, but the tensor is v. No, here the tensor is not differentiated, but v is differentiated, and some two indices, and here something like something similar. So you should fill the explicit indices from this table, but it should be structured like that. Yes, you see that v is differentiated here, and a is not differentiated. So g is not differentiated, just with some indices, and v is differentiated. Notice, by the way, that if we compute it, it is quite important, this observation, that if you compute Lie derivative with this in the direction of v of any a, you have at the coordinate expression, you have both derivatives of components of a and of components of v. Yes, this expression makes differentiation of components of both objects. So, for example, here, this is vk gij, comma k. Yes, so here g is differentiated. Here v is differentiated. There is a special important case which can be seen from here, that what is Lie derivative of a vector field. And so Lie derivative of a vector field is this result I derivative with respect to I. And what is it? It is v. This originally was v, say v I derivative with respect to I. Yes. So we see that the first term is v applied on w I, and the second term we have one upper index. So it is like the second part of the story, some object like that, and do the computation yourself that compute the analog of this term if A is just a vector field, not 1-1 tensor. Okay? So just for the upper index, what happens? And you will see that what happens there is this. Check from the table. It is of course, a very simple computation that you will look at the table or repeat the computation once again. And you will obtain something which is not that easy, but you will see that it can be rewritten to this form. So altogether is V Wi minus W applied on Vi derivative with respect to I. So don't forget to check the second term, yes? And this is interesting result from several points of view that, for example, you see from this bracket that it is skew symmetric with respect to V and W. Yes? Here it is not visible at all because W is the object of differentiation and there is Lie derivative where you have V. So it is not clear that this should be minus LW applied on V. It is not clear. But when you compute it, you see it. Now, what is it? We can independently compute something different, and we will see that it is exactly this object. So imagine that you have two vector fields and apply them on a function. What we get? Here is a function, here is a function, here is a function. So altogether it is a function. And what function? This one, by definition. So what we see that we applied altogether second order differential operator on this function. Yes? Because now what is this? Here is the derivative which is applied on a product of two functions. The first one, the second one. So it is applied on the first one is Wj, comma I, and the rest. And the second is plus W left alone, and the second derivative Ij applied on psi. Then, if you apply it, so altogether we see that it is really a second order differential equation, differential operator. So application of two first order differential operators consecutively gives you naturally second order operator. Yes? Here are second derivatives. But if you do it in inverse way, first V and then W, and compute it, you will see that the second term is the same. Check. Yes. Here, what is the first term? Here, W, so it is W, I, V, J, I, derivative with respect, and plus this same object. Here is what? Here is application of W on Vj. Now, what is highly non-trivial? That if you do a difference of these two expressions, if you subtract the first minus second, this second order term cancels. So, the both parts are second order differential equations, but their difference is just a first order differential equation. But all first order differential, not equation, but operators, differential operators, are vector fields. Yes, if you have first order differential operator applied on function, you applied a vector field on the function. So, and what is the difference? So the difference v psi minus w applied on v psi is the first object. Notice that again, combining this and this is just application of v on wj. So it is v applied on vi, I will rename. Here is vj and derivative with respect to j. So it is vi minus w applied on vi derivative. Yes. So I renamed in the final formula j to I. But what is it? It is exactly this Lie derivative. Applied on psi. This is a vector field. Yes, so this vector field is with these components. We just computed that it is a Lie derivative of w applied on psi. And what is here? By definition, this is called a commutator of vector fields. This commutator is meant like commutator for operators that apply first and then second and then reverse. So definition of this applied on psi is this expression. And now because the psi is the same, we have important formula. This one. So first of all, we discovered that from two vector fields, you can compose the third one by this operation when applied on function, which is called commutator. We will discuss it later also. And second, that Lie derivative of of w with respect to v is exactly this commutator. Yes, so we first didn't know that something like commutator of vector field is possible. Now we see it, that this cancels. Yes, when you subtract it, it is highly non-trivial. And the second, that this is exactly Lie derivative. And as I told you, here you can see from this definition explicitly that this is skew symmetric with respect to interchanging of v and w. And here it is not clear. Yes, but it is true that this is anti-symmetric. So this is just a special case of Lie derivatives of some tensor field, namely of vector fields themselves. And the result is a bit surprising, that you can write it in different way, which is useful. This kind of commutator, which is composed here, is well known from commutators in quantum mechanics. Yes, that you computed the commutator, for example, of Li, Lj in quantum mechanics, angular momentum operators. Yes, what are these operators? They are first-order differential operators. Yes, recall that Li is proportional to epsilon ij k x j derivative with respect to k. So, first order differential operators. What does it mean? First of all, these operators are vector fields, nothing else. And if you compute their commutator, you actually compute the commutator of two vector fields according to this formula. So you already, if you did some computations of this type, and also pi is just this derivative, again, vector field. So you already know the concept of commutators of vector fields from first semester quantum mechanics. And now we learn that there is a general theory around that. The commutator of two vector fields is again a vector field, so it makes some light on these commutators from quantum mechanics. We will study something which is usually called that geometrical interpretation of commutator, maybe next lecture, which is very interesting and very important, that what happens geometrically if this commutator is zero and if this commutator is non-zero. Yes? If it is non-zero, it is some vector field, and the resulting vector field has some meaning in differential geometry, and we will study it in general. And it can be backwards applied on this situation from quantum mechanics. That, for example, you know that this is non-zero, yes? There is some result that 1, 2 is proportional to 3. What does it mean geometrically? We will understand in general. And then we can apply it to, for example, this situation and see what does it mean actually that L1 and L2 do not commute. What happens there because of this simple fact? Okay, now I will have a look. What is the next to be explained? Yes, general. Yes, there are some properties of Lie derivative. Many of these properties we already used, but still there are some more. But maybe I will now go to something called exponent of Lie derivative and leave these more general properties to a later time. So now I will speak. I know that we already are able to compute any Lie derivative of any tensor if we need, yes, from the table. And we also know that what is Lie derivative of vector field. Now, exponential or exponent of Lie derivative. It is very useful techniques. Let's have a formula which is well known. So Taylor expansion of a function of one variable. And we'll try to understand it differently, and we obtain some strange formula, and then we'll prove that this strange formula is true in general, not only in this case. So first, imagine that we have a manifold of this axis. So our manifold is just a real line, and x is a coordinate there. And we have vector field there, which is just the basis vector field. So its flow is that x goes to x plus t. Yes, we know it already. If you don't see it, compute. So, therefore, here, it can be written as phi t applied on x. And f of phi t applied on x is composition. And what is it? It is just a pullback of f computed on x. Yes. And now, so the left-hand side can be written in highly scientific expression with pullback with respect to flow. Yes, this guy. Now, here is fx plus t. And what about this? It is just application of v on f. Plus t squared. What is the second derivative? It is 2 times applied v on f and 3 dots. Because v is just partial derivative with respect to x. Now, what is this? It is Lie derivative of f. So, what is this? It is Lie derivative twice applied on f. It means that Lie derivative of Lie derivative, of course. Yes. So, what we see that without x, it can be already written like f plus t, the derivative of f plus t squared or 2 factorial, the derivative of f, and so on. Or some operator applied on f. What is this operator? Here is just unit operator. Here is LV, TLV, plus t squared or 2 factorial LV, LV, plus dots. So this operator can be written in this way because it is applied on common f, which is arbitrary. And what is this series? It is series of exponential, yes? So it can be written as exponential of TLV applied on f. So this is some operator acting on functions. And definition of this object is this series. It is very similar like the definition of exponential of matrices, which already met in Lie algebras. So the final formula that this can be written as phi t star equals to e to t LV. Of course, we proved it only in our special case, when manifold is just R, vector field is this one, and so on, and the tensor field on which it is applied is just a 0,0 tensor F. So in very, very specific situation, this is true. And, well, first, is it interesting for physics that usually this Taylor expansion is not done, well, in the first year maybe, that you can define some functions in terms of infinite Taylor series, yes? But in physics, it is not very often used in this way. What is the typical situation when you use Taylor expansion? When you expand just few terms of your function, that your function is already known like sine or cosine, and you do expansion just first 2 terms or something like that, because this t is small usually. So exactly for this reason, this formula is interesting, because you can approximate phi t star by some several Lie derivatives if t is small. So this is the importance of the formula. But now the crucial question is that does this formula apply also in other cases like this, our trivial case? And the surprising answer is that yes, it is actually a general formula. Okay, there can be some limitations from some deep properties of vector fields and so on, but in typical situation it does hold. And I will do one proof here, which is not completely mathematical proof, but more or less, that we will compute first what is d over dt of phi t star. And then if we understand this result, we will use it and it will be very quickly. I just want to say that there is also another possible proof, and maybe also several others, which is based on some property of vector fields, which is called straightening out lemma for vector fields. And it is some property that any vector field which is non-zero in some point, it's a manifold with a vector field, and here at M you have Vm, which is different from 0, and it is a smooth vector field. Then you can find coordinates that exist, coordinates in which the vector field, which is in general like that it is just of this form. Yes? In proper coordinates in a neighborhood of this point where it is non-zero. There is a mathematically very deep and complicated proof of this fact. So what this fact says, that the components of your vector field in very, very technically chosen coordinates, complicated way, can be written like 1, 0, and 0. Yes, it is extreme simplification of your vector field. If this is true, what does it mean? That if you write it symbolically in this plane, this vector field looks like that. Yes, the flow of this vector field is just that x grows linearly and all other coordinates are still the same because there are no components. So if you try to write equations for flow, you will see that they are extremely simple and the flow goes like that. So there is a deep theorem in the mathematics called straightening out lemma, which asserts that if you have a manifold and vector field non-zero in some point, in vicinity or in neighborhood of this point, you can find very special coordinates, local coordinates, in which your vector field looks like that. If we apply this theorem for this situation, you can check that it is the proof of this theorem is practically this one. So it is you can try to assume that my vector field is like that, and then apply it on any tensor field, and you see that if you know this proof of this formula for just Rx and this vector field and so on, very specific case, you can prove it in general. So there is also alternative proof, like I will do now, but it is based on this lemma, which is very complicated. There are textbooks on ordinary differential equations in which half of the book is devoted to this lemma, and then the rest of the book is using of this lemma, then quite simple or the deep results can be proven in terms of this lemma quite easily. Yes? So the hard part of the proof is this lemma. That's why, of course, I will not do it here. Yes. But I just mentioned that sometimes it can be useful for you to know that such lemma exists, and when you want to prove something in local coordinates, you can assume in your situation when this happens, these coordinates, and the proof can simplify a lot. Now to the second possibility, that remember that Lie derivative is defined in this way. So now the question here is, what is this expression if we do not evaluate it at t equals 0, but at arbitrary t? It should be something dependent on t, and when you put t equals 0, you will obtain Lie derivative, of course. But what about this expression without this evaluation? So it can be rewritten as t plus s star. This is more or less trivial. It is from the definition of any derivative. What is d over dt? It is this. But now this is phi, say, s and phi t. Pull back also inversely. Which is phi t star and phi s star. So when we do d over ds, here is not s, it is a constant with respect to s. S is just here. And now it is nice that we evaluate the derivative at 0. So what is it? It is just jump over this part and do d over ds of phi s star, which is Lie derivative. Yes, because it is already evaluated at 0. So we have an important result. That d over dt without evaluation at 0 of phi t star is phi t pullback and composed with Lie derivative. This holds on any tensor field. So does it, is it true this original formula for t equals 0? We have this 0, which is unit operator. So it is unit operator composed with LV, it is LV altogether. Yes, so it is true, this one, as a limit. Now, what about the second time derivative? What scientists discovered that second derivative is the derivative of the first derivative? Yes. So it is d over dt of this. So it is d over dt of phi t star and then LV. Yes. But d over dt of phi t star is phi t star LV and then LV once more. So we already see that d over dt nth repetition is phi t star LV nth power. And then what about evaluation at 0? Now, when we already did these derivatives, it is the right-hand side evaluated at t equals 0, which is unit operator composed with this Lie derivative. So it is Lie derivative applied n times. So it is nth power of this operator. Now, why it is useful? Imagine that we compute phi t star, and imagine that this t is our variable, and we do a formal Taylor expansion. It is at Taylor expansion around 0, t equals 0. So it is what? It is this plus d over dt at 0 of phi t star plus second derivative, the second derivative here at 0, and so on. So just formal expansion of this operator with respect to t. Here it is unit operator plus t, it is Lie derivative, plus t squared over 2 factorial of Lie derivative squared, and so on. So altogether it is e to t of Lie derivative. Of course, this is not very nice functional analysis done here, but just a formal computation. So we see that we can use this formula where needed. And as I told already, this formula is usually meant that what about t equal to epsilon for small values of t, that it can be written like unit plus epsilon LV plus epsilon square or 2 factorial LV LV plus 3 dots. Is that typical application of this formula is not to take the whole series, but to take just a few terms. It depends on how many you need. And you have an exact formula, so to speak, for approximation for small epsilon. So you can compute, for example, the pullback of infinitesimal flow with accuracy to first epsilon, with accuracy to second epsilon, and so on. And you know what the objects are there, yes? Near epsilon, epsilon squared, epsilon third power, and so on. It is very useful to compute some expressions where Lie derivative, or where these small pullbacks are necessary to some accuracy, and you can obtain interesting results that to the 0 epsilon, it is like that. To first order accuracy, it is like that. So some interesting phenomena come already to your computation as a first approximation of this formula, but there are also interesting phenomena which we will see when we compute interpretation of what is a commutator, that what is the geometric meaning of commutator when we will study. We will need this formula, for example, up to this accuracy, because the first accuracy will give you nothing interesting, but the second order accuracy gives you very interesting result, which enables us to understand what is the commutator geometrically. And now maybe I will finish this lecture with one observation, some small theory about concerning frame fields, that we already had this concept of frame fields, you remember, yes, that we can introduce frame field in this way, and dual frame fields in this way. So what are these objects? They are n by n matrices, in terms of which you can scramble the coordinate frame field and to obtain some other frame field. Because frame field is a basis, so frame in each point. And we have coordinate basis in each point, but from linear algebra we know that it is not necessary to have one particular basis, that you can go to other bases in any point. So this is a mixture or scrambling of this basis different in each point. Yes, and this is dual basis to this, and also this is dual basis to this. And now the question arises, natural, that we know that it is possible, and the question is, do they exist coordinates other than x's such that if you construct any frame field, that it is just another coordinate frame. Yes, that the question is whether they are whether they exist frame fields which are not coordinate. Yes, that they do not exist coordinates such that your frame field is just coordinate frame field with respect to these other coordinates. And we will see perhaps tomorrow that very important thing in order to answer this question is to compute commutator of two vector fields. That is a concept which we learned today. What is a commutator? And why it is important? Because what is the commutator of coordinate vector fields? If we apply it on a function, what is it? By definition, it is this. From the definition, what is a commutator? But what is this? It is the difference of the order of partial derivatives on a given function. But we know that on smooth functions, it doesn't depend on the order when you do partial derivatives. Yes? So it is zero. It is knowledge from first or second year on analysis. So this is always zero, this commutator, for any coordinates and resulting coordinate frame. And if you have some frame field, and if you compute that here is non-zero, then of course your frame field cannot be coordinate frame field, because all coordinate frame fields have zero commutator, mutual commutators. So now the situation is like that if you have a frame field with non-zero commutators, you know that it is non-coordinate frame field, that no coordinates y exist for which this happens. Yes? But then it is also interesting question, and what about the situation when here comes zero? One possibility is that this is because it is coordinate. But we do not a priori know whether it is the only possibility. That is zero here the proof that our EA is a coordinate field? Yes. So this is not clear at all. What is clear that if it is coordinate, it is zero, but the converse statement is not clear. And the result is that if they are local frame fields, it is true, yes, that this is already guaranteed that such coordinates exist. It can be it can be done, this proof, in terms of this language, of terms of vector fields, but it is a little bit unpleasant. So we should wait to the second part of this course, mathematical physics, when we introduce concept of differential forms. Then there is one theorem called Poincaré lemma for these differential forms, and very indirectly we will see that not in this language, but in the language of these objects, these covector fields, which will become so-called one-forms next year. So in terms of these one-forms or covector fields, and operator of D, which will be generalization of our D, and some theorem for this D, we will see that it is quite simple answer that this is really true. Yes, so I will not do proof here because it is cumbersome in this language, but it is nice and elegant in other language, which we will have next year. So I just postpone the proof of this fact to next year. But the fact itself is interesting and important. So we should know 1 year before proof that in order to check whether your frame field is coordinate or not, you should just compute all elements of commutator of AB. That means that all commutators for any A and any B on your frame field. And if you see somewhere non-zero element as a result, it is very simple. Your frame field is not coordinate. If you find always zeros, by this theorem, we know that it is coordinate already. And by this theorem, by the way, you can also find this coordinate. In what coordinates this happens, which is quite nice. So, for example, let's check some particular situation. We remember that in xy plane, we can, for vectors, have either this basis or this coordinate basis. It is with respect to Cartesian coordinates or with respect to polar coordinates. And we remember that Gij for this particular, here Gij components of metric tensor is just unit matrix. So it is orthonormal basis. And here it is 1, 0, 0 r squared. So it is not orthonormal basis. But we can improve it. How? I recall that G in these coordinates comes to be like that. And this term can be rewritten as r d phi cross r d phi. So if we call this E phi, and if we call this ER, we have ER plus E phi. So this is already orthonormal coframe, and the corresponding orthonormal frame is this and 1 over r derivative with respect to phi. We had this computation already on the blackboard, yes? It was at the times when we studied metric tensors and so on. Now, the question is, this frame, which is just the frame with respect to coordinates, but improved by this factor in order to be orthonormal. Yes, so now it is orthonormal. And the question is whether there exist coordinates, whether it is coordinate frame. So whether there exist coordinates in which this is derivative with respect to some first coordinate, and this is derivative with respect to some second coordinate. Because if such coordinates existed, they would be very useful. Yes, they will be improved polar coordinates. But you remember that you have no improved polar coordinates in the first year, so probably they do not exist. Now, how we check? We should compute the commutator of this vector field. So, if applied on psi, it is what? It is this derivative of 1 over r of this derivative minus 1 over r derivative with respect to phi applied on derivative with respect to r. Now, this is first derivative of this function, which is minus 1 over r squared, and nothing with the second. Plus 1 over r derivative of phi, of psi. Now you see that this cancels. And what remains there is 1 over r squared, derivative with respect to phi, applied to psi. So, this commutator is this vector field. And this vector field is non-zero. So, would we see that it cannot be true that this is the derivative with respect to some first coordinate and second coordinate? Because such coordinate cannot exist, because this commutator should be zero always, as for any pair of coordinates, yes, in this case. So we see that already at this elementary level, when we compute orthonormal frames in a plane, we already meet a frame for this one, which is rather complicated. It is non-coordinate frame. There do not exist coordinate, that the first one is the first derivative, the second is second derivative. It is better than the coordinate frame because it is orthonormal, but it is worse because it is non-coordinate. Yes, so you have to pay something for this orthonormality in this case. So, thank you.